will be available via Sched and YouTube a few weeks after the summit. We will be saving all questions for this session until the general Q&A period at the end of the session. Please use the Q&A box to enter any questions you may have for our speakers, and we will discuss them after all of our speakers have presented. And Caitlin Tucker from PDE will be helping out with our Q&A session today. So thank you again for joining this morning's session, and I'm now going to throw it over to Marjorie Kaplan to introduce herself and our first speaker.
Good morning, everybody, and welcome to our session on climate change in the Delaware Estuary. We're so excited that you joined us today. I'm Marjorie Kaplan. I'm the Associate Director of Rutgers Climate Institute, and I also serve on the Delaware River Basin Commission Committee on Climate Change. So I'm very excited that you could all be here today. We have 5 fantastic speakers. So let's just get started. Without further ado, I'm going to invite Dr. Danielle Krieger to join us first, and she will be speaking on climate change indicators in the technical report for the Delaware Estuary and River Basin. Dr. Krieger is an ecologist with more than 30 years of research and teaching experience. She serves as science director for the Partnership for the Delaware Estuary. She coordinates scientific programs, collaborations, peer review, and support of the Delaware Estuary program. And she is also a member of the DRBC's Advisory Committee on Climate Change. So take it away, Danielle.
Thanks, Marjorie. Can you hear me okay?
Yep, you're great.
Okay, great. Well, I thought to kick off the sessions part of the climate forum, it would be helpful to, I guess, get our juices flowing by seeing some actual climate change data. And at the Delaware Estuary program, every 5 years, we coordinate a State of the Estuary report that is based on a technical report called TREB, or the Technical Report for the Delaware Estuary and River Basin. And, before I get into some data, I just want to say that, we've been working on climate change and climate adaptation work for quite some time now. About 10 years ago, we worked with many partners to explore how climate change would affect key water, habitat, and living resources, such as drinking water supplies, habitats such as coastal wetlands, and living resources such as bivalve shellfish. And since then, we've worked on an ever-broadening array of programs and actions, from outreach and engagement, such as our Weathering Change sign-on pledge targeting elected officials and the public, to our growing array of scientific monitoring and restoration programs. But really, one of our most broadly useful contributions is to coordinate this State of the Estuary report. And DRBC has been one of our core partners from the get-go. We also work with many university folks and state, federal, and local agencies. And the report basically describes the status and trends of about 60 environmental indicators, and they're organized into 8 chapters in the TREB, or the report, which is about 400 pages. Example indicators are listed under each chapter here. But one of the chapters is on climate change itself. And, we also cover climate change throughout all of the other indicators in the report where they affect other important resources. And so we developed this technical report first, and it's really aimed at environmental professionals. And then we do a public translation product where we cherry pick, a subset of the indicators, those that resonate more with the public for outreach. So, of course, in the Delaware River Basin, we are focused on the main drivers of climate change and how they affect resources. And really, I wanted to point out that special nature of the Delaware River Basin is that we have this large freshwater tidal prism. So it's not just sea level rise we're concerned about, which we just heard, the wonderful plenary by Ben Harrington, but salinity rise, because again, from Wilmington, Delaware to Trenton, it's tidal, it's coastal, but it's freshwater. And that salinity regime is very important. So before I get into the data, I just want to acknowledge that the climate change chapter of TREB, every chapter is authored by, folks mainly outside PDE and DRBC. So Ray Najar from Penn State has been the main architect of the climate change indicators, working with Andrew Ross, who was at Penn State, now at Princeton. and Sue Killam, who chaired our stack for over a decade and is from Drexel University. So just these are teasers, really, just snapshots. I want you to just know that this report exists and that these data exist. What are the temperature trends in the past for the Delaware River Basin? Across the watershed over the past 100 years, of course, we've seen more than a 1 degree C rise in temperature. And importantly, the slope of this trend line has increased since the 1980s, if you can see to the right in the dashed line. The report also shows some raw data. Here's a plot showing the differences in temperatures in the upper watershed versus the lower watershed in the blue and green, respectively. And you can see that the recent trend maybe start slightly steeper slope in the upper basin compared to the lower basin. Of course, temperature affects so many natural resources in complex ways. One of the more recent TREB climate indicators is the frequency of ice jams on local rivers. These, of course, have been decreasing since the 1930s. They do still occur periodically on the Delaware River, shown here in red bars, but becoming less frequent. Changing temperature, of course, affects the biology and chemistry in so many ways. We know warmer temperatures hold less dissolved oxygen. And you need to start thinking about the seasonality of these increases, such as the case, an example of when you have early rapid warm up in the spring, combined with higher spring nutrient runoffs. Nutrient loads increase, fueling algal blooms, potentially causing fish kills. This is something that maybe we don't think as much about here in the Delaware Estuary compared to other systems, but we have seen some early warning signs. This is actually from 2010, where such a scenario led to a fish die-off in the bayshore of New Jersey. Of course, precip is also increasing, trending up, similar to temperature, about a 10% increase over the longer time series, but a more recent increase since the 1980s. And if you dissect this down and look at seasonality in the upper left, winter, spring, summer, and fall in the bottom right, you can see that the temperature increase has been actually a bit more pronounced in the fall and perhaps in the recent time series in the summer as well. Well, precip, of course, matters for things like stream flow. And this, I guess, these data are annual means. So yes, we've seen an increase in stream flow, and yes, the rate has been increasing a bit more recently. But I want to emphasize that a lot of this precip has come in buckets. Warmer air holds less moisture, more energy, atmospheric energy for storms. So this doesn't really capture the more anomalous big flood events. But we know that the increase in impervious surface in the basin combined with flashier runoff events is leading to more flooding. TREB also has some other cool, I think they're cool indicators. What about snow cover? This is a very messy plot. Don't have time to get into the weeds. I just want to show that snow cover actually has not shown a significant trend over the period since the 1970s. But there's a lot of interactions going on here. You have the warming temperature, you have increasing precip, but you also have the weather events connected to the things like the NAO, the North Atlantic Oscillation, which the black line here has shown an increase in the NAO, and that could also be maybe counteracting the effects where you get big snowfalls in certain years that affect the snow cover. Another novel indicator, I think novel, is wind speed. Did you know that wind speed has actually been dropping in the Delaware River Basin? This change in annual means may go unnoticed when we have increases in dramatic storm events like Hurricane Sandy. But this also affects the ecology in many ways. For instance, one of our past summit plenaries, Scott Nixon, published a great paper about how slowing wind speeds in Narragansett Bay led to increased fog. And the increased fog shuts down phytoplankton blooms, and that caused the collapse of bivalve fisheries. So wind speed, how it affects transpiration rates of forests. I mean, that's something to also be paying mind to. Of course, we're going to hear a lot of talks. We just heard a wonderful plenary on sea level rise. And I want to throw in there for us, it's also salinity rise. There's a series of great talks at the summit on salinity rise and the changing salt line in the Delaware River Basin. I'm not really going to get into this much, but I think that the important thing that at least I've been kind of focused on with sea level rise is the changing rate of sea level rise. If this were expected to be a linear increase, many natural resources might be able to adjust, but with the changing rate, there are these tipping points, and such is the case with coastal wetlands. So now we're going outside the climate chapter of TREB. There's a chapter on aquatic habitats, and coastal wetlands are covered in there. And for some time, we at the Estuary program have been very focused on coastal wetlands and the rapid loss of wetlands in the system. We talk about the nature of the losses. There's most of the losses have been via edge erosion. We also, periodically in some years see interior drowning, where you might be having a vertical, not keeping pace with sea level rise vertically. Don't want to get into that here. The next couple talks are going to be talking about this. But just to say that coastal wetlands, whether they keep pace with sea level rise, it's complicated, very complicated, lots of factors. But getting back to the tipping point question, once we hit 10 millimeters per year and beyond, I mean, most wetlands internationally, coastal wetlands really can't keep pace, or they can keep pace up to about 4 to 10 millimeters per year. What happens when we eclipse 10 millimeters per year? We've done projections. This is way back in 2010. We looked at SLAM modeling, and we're projecting maybe a gain of 40,000 acres of upland or wetlands moving into uplands and ag areas, but you're going to lose more than 100,000 acres at the water's edge. So that's a net loss of coastal wetland acreage. And because coastal wetlands are a foundational habitat feature of the Delaware estuary, supplying so many stacked ecosystem services, more than other habitats, that the habitat conversion is going to lead to a net loss of ecosystem services. So that's important for water quality and fish habitat and shell fisheries and carbon capture. TREB also talks about climate change effects on shellfish, just as in examples. Oyster reefs, mussel beds, of course, they help to stabilize erosion, help to attenuate or provide coastal resilience. They also filter a lot of water. Let's work in freshwater mussels. There's different types of bivalve shellfish. So in North America, freshwater mussels are already the most imperiled fauna, but climate change, threatens them in different ways in the Delaware River Basin. You have the salinity intrusion into the tidal freshwater, which is going to deplete mussel habitat. Stormwater events scour streams, major impact on mussels. Of course, oyster populations are hard hit by 9 native disease agents, and salinity rise favors those disease. And perhaps the biggest filterer or water quality improvement organism in the system from a bivalve standpoint are ribbed mussels in salt marshes. And as you just saw, we're losing their marsh habitat. So we're losing about 100,000 ribbed mussels per day.
We have about a minute left.
Thank you. So of course, climate change has some upsides, increased growing season, or oysters have a niche expansion into the intertidal. But really, climate change prognosis, as per TREB, is that the system is already changing pretty dramatically, and the net effects of future climate change will be very problematic for these habitats and the resources that support a $10 billion water economy in the Delaware River Basin. We're launching into TREB 2022. We're inviting authors contributing and peer reviewers now. Please, if you have expertise to bring to bear on this report, contact Leanne Hoff at PDE. And just to wrap up, TREB is available and it analyzes a lot of cool data for key climate change indicators that affect natural resources in the Delaware River Basin. Not all these changes are going to be bad, but there will be, we're projecting more losers and winners. So to sustain clean water, clean air, key ecosystem services, we really need to understand these complex scientific interactions, ecological interactions, and that's what the summit's all about. Finally, resource management goals really need to plan for change. There's a lot of traditional management paradigms where you can only restore to historic conditions, for instance. We need to be thinking of future sustainable conditions. Thank you.
Thank you, Danielle. That was fantastic, as always. And we will look forward to communicating with you during the Q&A session. So now I'm going to invite Dr. Fenghui Chen to join us and to start sharing his screen. Fenghui is a senior water resource engineer with the Delaware River Basin Commission. He's going to speak to us about sea level rise impacts on Delaware estuary wetlands and marshes. He has more than 20 years of experience in water resource engineering and fluid mechanics and environmental hydrodynamics, sediment transport modeling, river ice hydrology, and oil spill modeling. And he has been with DRBC since 2018. Fenghui, take it away.
Okay, thank you. Good morning, good to see everyone. Thanks for having me. Thanks, Daniel, to give a lot of cover on the climate change. One of the consequences of climate change is the sea level rise. So my presentation is about potential sea level rise impacts on the Delaware estuary wetlands. So according to NOAA TED data from Lewis, Delaware, the sea level rose approximately 0.35 meters over the course of last 100 years. But the rate of sea level rise may accelerate in the future with the sea level rise, with the climate change. So sea level rise not only will affect the salinity intrusion and pose threats to the drinking water intakes near the Philadelphia area, it may also harm the estuary wetlands that dominate by the marshes surrounding the Delaware estuary. So in 2018, the DRBC proposed a salinity modeling study to evaluate the impacts of salinity intrusion in response to the sea level rise. Since then, a three-dimensional hydrodynamics model using the environmental fluid dynamics code supported by EPA has been developed and preliminarily calibrated. Well, the model will still be validated with more data coming in that being collected by USGS and NOAA. So this is ongoing efforts. So in this presentation, the impacts on the key environmental parameters associated with the sea level rise in marshes will be discussed. So the tidal marsh usually can be delineated according to the horizontal salinity gradients. So as described by Reed and others, as you can see from the mouth of the bay moving towards upland, you see the red color is the salt marsh and change to a brackish marsh and then gradually change to freshwater marsh in green. So why marshes are important? So tidal marsh wetlands serve many important functions. I'm not going to go through all this list here, but I want to highlight one point related to the climate change. So this is according to NOAA. So these coastal marsh wetlands are incredibly efficient at absorbing and storing large quantity of carbon dioxide from the atmosphere. So they are actually sequestering carbon at a rate of 10 times higher than the most forest areas. So they are incredibly efficient natural carbon sink. So sea level rise. So we have reviewed multiple sea level rise studies and proposed by, we have proposed 5 sea level rise scenarios for our 2060 planning time horizon. So most likely range, let's say from 10% to 90% chance of sea level rise for the Delaware estuary, maybe range from 0.3 to 0.8 meters, with 0.5 meter being the median for year 2060. So sea level rise values mentioned here, I want to mention that is reference to the 2000 baseline mean sea level at the mouth of the bay. And the sea level rise here, we are refers to the local relative sea level rise with respect to the land elevation or with respect to the channel depth. So the vertical motion, like land subsidence or some short-term processes like sediment consolidation, groundwater withdrawal has been considered. So here you see on the left is the US land cover database 2016. So here the cyan colored area along the shore, along the bay shore are the wetland dominated by tidal marsh. And the top red line in the middle of the graph here is separate the RBC water quality zone 5 and zone 6. Zone 6 is for the bay area. So it must be noticed that the shoreline may erode and marsh may migrate further inland due to the sea level rise. And those processes are very sophisticated and not directly modeled by our model. Review some other researches, and they found that during the last 5 decades, the wetland has been lost at the rate of approximately 1 square kilometer per year. And the land cover analysis between 1975 and 2018 shows that roughly about 43.5 square kilometers of tidal wetland have already been lost to open water. And there are some other limited data regarding the shoreline erosion, and it's about like 3 meters per year for the entire Delaware Bay shore. That's a limited data available there. And on the right, this is our model domain in the, we are focusing on the Bay area, and we have 7 sub areas that we going to focus on today. In the following slides, I'm going to show some model results, just focusing on those areas. So first of all, with the sea level rise, more water, ocean water will coming into the estuary. So let's look at the water volume first. So we can calculate with the model, right, how much water may move into the estuary and move into those marsh areas, and what's the volumetric ratio of that amount of water with respect to the total water volume in zone 6 open water areas. So as you can see, as with the sea level rise, more ocean salt water will come into the estuary and flood into those marshes. And meanwhile, the relative amount, relative percentage of that water volume also increase. So this tells us that the overall tidal prison will increase with sea level rise. And this has profound impact on the overall estuary hydrodynamics and salinity intrusion. But I don't have time to spend on that topic. But let's go back, just focusing on the local environment in the marsh areas for now. Secondly, let's look at the water surface elevation. With the numerical model, we can look at like over the long-term period, what's the tidal range? Okay, this is an example. We have a cross-section cut at the river mile 37, which is about the location Shipjang Shoal area. And the 3 blue lines there represent highest, lowest, and mean water surface elevation predicted by the model. So, and from left to the right is for various of sea level rise scenarios. This is one year period. So as you can see, with the sea level rise, some low-lying areas may become more frequently flooded or permanently inundated. We can also, with the model, we can select a specific location and look for more details. Let's, for example, we select 3 locations along the Jersey shore here. So this is the predicted water surface elevation for 1 month period, and at those 3 locations for the baseline condition. So the background gray lines represents water surface elevation predicted in the navigation channel that is close to the selected location, so that you can see the full tidal range. And on top of that, the blue line represents water surface elevation at the selected location. So the blue signals indicate when area was flooded. And you can see there's a stagnant horizontal segment of that blue line that indicates when area was dry and the land was exposed. So as you can see under the baseline condition, these areas only got flooded twice a day during the high tide spring tide, and then for just a short period of time. So this is the same 3 locations with 0.8 meter sea level rise, which is about 2.6 feet. As you can see, the time duration that the area being underwater become longer with the sea level rise, and the water depths also increased during the period of inundation. Both the water depth and the inundation frequency will have profound impact on the marsh habitats for various plant and animals that taking shelter there. So it will affect plant zonation for the low marsh and high marsh areas. I apologize for the background. Sorry about that. We can summarize the model results in various ways. This is, well, the phone is from the school. It will be over shortly. So here is an example, the inundation frequency plot. Let's just take the table, for example. Apologies for the small font size. So if you take location 2 and 3 for the north, under baseline condition, those areas only inundated 15% of the time, which is like 3.6 hours a day. And with the 0.8 meter sea level rise, the inundation frequency will greater than 50%, which means longer than 12 hours a day. So this is the predicted salinity. So we have looked at volume, water depth, water sublimation, inundation frequency. So let's look at this is one of the important environmental parameter. So again, we are looking at a very large spatial and temporal scale. This figure presents spatial distribution of long-term average salinity based on 1-year simulation. If you're just focusing on the shore area, you can see with the 1 meter sea level rise, which is on the right, compared to the left is the baseline condition. So you can see the salinity level increased. So we can quantify this a little bit more. And this figure summarizes the predicted long-term average salinity over 7 marshes, okay, from the left to right, marsh number 1 to 7, which is from the mouth of the bay towards upstream. So the color code here represents various sea level rise scenarios. We have 5 scenarios. And what you see here, 2 things. First, you have basically 2 environmental stress on the marshes. One is the horizontal gradients. So clearly you can see a horizontal gradients in the salinity from the mouth towards upstream, there's downward trend. And then secondly, you can see the vertical gradient. So for given marsh areas, right? And you can see the tidal average salinity increases with the sea level rise. And you can also dive into some specifics. For example, marsh number 1, with the 0.8 meter sea level rise, you can see the medium salinity actually increased by 5 ppt, something like that. So again, sure. This is the mass loading. I'm going to skip this. So in summary, a numerical model simulation indicates that sea level rise may significantly alter the environmental parameters in the Delaware estuary wetland. So as sea level rise, the amount of water get into the marsh areas and inundation frequency, water depth all increases. And sea level rise also change the salinity regime in marsh wetland. That may have profound influence on the health of the marsh habitats. So then next step, ecologists or biologists may take the physics predicted by the model and they can make their own assessment for the ecological effect of the sea level rise onto marsh areas. That's pretty much conclude my presentation. And you have more questions, feel free to contact me. Thank you.
Thank you, Feng Wei. That was very interesting and disturbing. And now
Apologize.
That's fine. I meant more the information. So now I'm going to invite Dr. Judith Wyeth to share her screen. Dr. Weiss is a professor emerita at Rutgers University in the Department of Biological Sciences. Her research focuses on estuarine ecology and ecotoxicology, and she's published more than 200 scientific papers, books on salt marshes, fish, crabs, marine pollution for the general public. And she's co-edited a technical book on biological invasions and animal behavior. She's a true treasure for those of us in New Jersey who've known Judy for a while, and we're so grateful that she could speak with us today on how the Delaware Bay salt marshes are faring in the face of sea level rise. So Judy, please proceed.
Thank you very much. I'm glad to be here. I come from the northern part of New Jersey, unlike probably most everybody else in this session. I'm giving you sort of a segment of a report that I chaired a committee of the Science Advisory Board of New Jersey DEP, and my co-authors for the report were Beth Watson, Beth Rabbit, and Chuck Harmon. We took a look at the marshes in New Jersey and focused on 4 major marsh systems: the Hackensack, the Meadowlands up here, Raritan Bay, there, number 2, Barnegat Bay system here, and Delaware Bay, number 4. We're looking at these in terms of how are they doing? Are they getting enough sediment to elevate at the rate of equivalent to sea level rise or better? And how are they doing in terms of acreage? Are they losing marsh area because of erosion at the edge? I mean, that's 2 choices. A marsh faced with sea level rise has to either or do both, elevate to keep up, and as sea level rises, it's possible to migrate inland. Many don't get enough sediment to keep up. With the sea level rise in New Jersey, I have it from Bob Kopp. As of 2019, it was between 5 and 6 millimeters per year. That contradicts what was said just before, that it was somewhere like 3 something. It's over 5. In developed areas in the state, for migrating inland is impossible because there's development. And so looking at this, we evaluated 4 potential remedies. Some symptoms of a marsh in trouble is erosion at the edge, as seen here, patches of subsidence and pans and pools in the marsh, and vegetation die-off from the persisting water that's supposed to be leaving the marsh at low tide that persists there. Looking at the Delaware Bay piece of our report, there's been a lot of studies looking at the acreage in the marshes of Delaware Bay, and these all took different time frames. So you see, we have lots of different time frames of looking at marsh acreage. At the net change in these various reports shown here over different years. But we can say there's a lot of erosion going on, but we can also say it's less than might be expected, because in the Delaware Bay, unlike the other 3 marsh systems we looked at, the marsh can migrate and is actively migrating upland into forests. This is not happening in the rest of the state. Here's some look at the erosion. This is Gandy's Beach in Delaware Bay. These red dots are showing the same location. So you can see in 1930, it was here, and by 2015, this was in open water. But 1930 to 2015 is a reasonably long time. Here is something from Great Bay, where Rutgers Marine Field Station is located. Here, this outer line is where it was in 1995. And here's where it was in 2015. So this is a much shorter time frame and considerable erosion being seen here. Looking at the vertical accretion in marshes, this is measured through surface elevation tables, or what's called sets. The sets enable you to look at the accretion of new sediments coming in from the water. Also, additional elevation from plant processes. And also, you can get measurements of what's going on that's taking away elevation from the marsh, namely subsidence, compaction, and decomposition going on down here. So you get, with the SET, you're getting how much accretion, how much loss, how much subsidence, and then you subtract the subsidence from the accretion and you get the net accretion, net elevation change. And here's a bunch of marshes that have been studied by probably a lot of people who are maybe sitting in and on this session. We thank Leanne Hoff for sharing this data with us. We have the net elevation change in the right-hand column, and there are 5 of these 12 marshes that are 5 or 6 millimeters per year. A star is indicating it's barely keeping up. A star is not like a star that's given to an A student for doing terrific. This is a star that's saying, meh, barely making it, and the others are not. The others are less than 5 and clearly not keeping up at all. So then what can we do about this? Well, we looked at 4 possible remedies, and I'll go through them one at a time. We talked about Delaware Bay is moving inland, which is really nice. And you guys are very lucky at Delaware Bay that you have undeveloped land right behind the marshes, into which the marshes can and are migrating. But there's so many other places that don't. The developed areas are meeting a phenomenon that somebody called coastal squeeze. It's a great term, I love it. Between not a rock and a hard place, but between the water and a hard place. And, they're running into developments. So you have either, houses, town right there, or somebody's built a bulkhead there and the marsh can't go anywhere. So what can we do about it? The idea is to create migration pathways, buy houses from people, protect this land, transfer property to the public, and remove the houses, remove the development, remove the roads if you can, to make space for the marshes to move into. Now, this is all very well in theory. In practice, you can imagine that this isn't all that easy to do, and it's in the purview of local towns and municipalities in terms of land use. And this runs into all sorts of social and political issues. So it would take a whole lot of education and changes of attitude to get this to be a widespread solution to the saving salt marshes. Another thing that we looked at was management of Phragmites. Phragmites is the plant that most people hate. It's an invasive species. It is reducing diversity of marsh plants, to be sure. And it is also removed all over the state in restoration projects where they remove it and replace it with Spartina. The view is that this is a useless plant and it's doing only damage. However, scientific studies for the past over 20 years has been showing that it does provide significant habitat for marine organisms. The studies on fish show clearly that mummy chugs, Fundulus heteroclitus, do not like Phragmites, particularly the larvae, eggs and larvae. However, other fish don't seem to care what plant is on the marsh surface. So when you look at all the studies that have been done and do a meta-analysis, they say there's a somewhat negative effect of Phragmites on nekton, is fish and crabs and such that swim in the creeks. And this varied. So it's not terrible, you know, it's a somewhat negative. The studies done on invertebrates, both the benthic invertebrates in the mud and the ones that crawl on the marsh surface, most of those studies find its equivalence in both types of marshes. And then other ecosystem services that Phragmites does, I put it in red because it's the most important one for our seminar today, is that it enables marshes to elevate faster and keep up with sea level rise better. This is done over 20 years ago. It builds the soil, it produces more litter, which traps more sediments and so forth. Also, the fact that it grows dense and tall, it provides better buffer against storm surge. Beyond that, it's better at sequestering pollutants, sequestering nitrogen, which will reduce eutrophication, and it's also better at sequestering carbon, which is called blue carbon, which is taken from the air into the plant and then sequestered in the soil, which is helping to mitigate climate change. So with all these good things it does, we say leave some there. Don't spend all the money killing it. Let's leave some there.
Judy, you have about 2 minutes left.
Okay, another thing we looked at is spraying sediment onto the marsh surface. This is called thin layer deposition. It kills the plants there, and it takes a while for the plants to either grow through the sediment or get replanted. Issue is how thick to make it and how soon before you have to do it again. There are 4 projects that were done, and I don't have the time to go into them in detail, on this thin layer deposition in South Jersey. And so we are learning about it. It's also possible to deposit sediments in the water itself and let currents bring the sediments onto the marsh. And this is being done in the Netherlands. It doesn't have the loss of ecosystem function like thin layer. Another thing that can be done when you've got pools on the surface is dig narrow channels called runnels that enables the water to drain into the tidal creeks. And finally, with erosion at the edge, and there's wave action, you get this undercutting, and you put something here. A living shoreline means you're putting something at the edge of the marsh that will help reduce that erosion. In Delaware Bay, with their use of core logs here and rocks, and you can see the time the marsh has come back. Also, they learned the core logs are not effective if there's much water movement. They don't last very well. Some harder structures that are being used are oyster castles. And you can see a picture here of oyster castles. So the conclusion, our marshes are at great risk from sea level rise, or they need to elevate fast enough. Most aren't. Few are elevating fast enough. Only Delaware Bay is migrating inland. The natural solutions, leaving frag or the migration pathways, requires a lot of change in education policies, political and social issues, and changing people's outlooks. The engineering solutions, that is adding the sediments and the living shorelines, are expensive, experimental, site-specific, and temporary, but both are showing promise. And I thank many people from the Delaware Bay area, including Leanne Hoff and Josh Moody from PDE, Johnny Crispy and Rick Lather from Rutgers, Tracy Quirk, Martha Maxwell Doyle, Francisco Artigas and Ildiko Peckman from the Meadowlands, and Mathia Yepsen of NJDEP, who was extremely helpful through all our work. And thank you.
Thank you, Judy, for that incredibly enlightening presentation. I am going to now invite Macy Shimon to join us. Macy, you can go ahead and start sharing your screen if you would. Macy is a graduate assistant from Villanova University, and Macy's going to speak to us about the impacts of salinity change on greenhouse gas emissions in marsh ecosystems along the salinity gradient in the Delaware River estuary. So Macy, we're very happy to have a graduate assistant with us today. So go for it.
All right. Just as a forewarning to everyone, my internet has been a little wonky today. I'm hoping it holds out for this 15 minutes, but everybody keep your fingers crossed for me. So as she was just saying, I have been spending a majority of my master's degree looking at the impacts of changing salinity on greenhouse gas emissions in tidal marshes, specifically along the Delaware. And in the hopes of not being too reiterative, considering we are all talking about tidal wetlands for the most part today, just a very brief background for anybody who happened to join a little bit later. So tidal marshes pretty well just serve as this barrier at where land and water meet, and they provide a lot of crucial ecosystem services. This was something that was also brought up several times too. So these can be things like flood mitigation and providing biodiversity hotspots, but specifically for my interests, what I'm looking at is more so the water quality functions. So tidal marshes do a really great job of filtering the water and removing nutrients from the water, and they also act as hotspots for biogeochemical cycling for carbon and nitrogen. And so the way that these services are performed, though, as we've kind of already touched on too, depends quite a bit on what's going on in the estuary. And so specifically, my interest is seeing how a change in salinity might impact how these biogeochemical cycling is happening, as well as the emissions associated with that, what kind of greenhouse gas emissions we might see. And so Danielle did mention earlier that we do have a large tidal prism in the Delaware River, which makes it pretty unique in some ways. And we also have issues with salinity rise as well as sea level rise. And so naturally, human activities over the last several decades between fossil fuel combustion and agricultural runoff have resulted in increased amount of substrate in these wetlands. So extra nutrients for these chemical processes to happen. And climate change also has its own impacts on these marshes. So we see that as patterns of precipitation start to change, as well as some of these sea level rise scenarios we've already seen start to happen, they can actually combine to move the salt line further up along the Delaware. And so the issue that we can see there then is not only this loss of marsh area and conversion of marshes into brackish and saltwater, we also see that this can influence how these biogeochemical processes are happening. And so what I've noticed quite a bit in my research prior to my setting up my experiment in and of itself is that a lot of people have actually already looked into carbon cycling as it relates to salinity and changing salinity. However, there's not as many studies that focus on the nitrogen part of the story. And this can be probably for a few reasons. Some of the studies that have already been done, it's pretty variable in response. So we see that nitrogen cycling can actually increase, it can decrease, and in some cases, there's actually no impact at all when people are messing with salinity and trying to see what types of nitrogen cycling is happening. But it remains pretty important for us to study just because nitrous oxide in and of itself is nearly 300 times the global warming potential of carbon dioxide. And over the last decade or so, it's increased about 18% in our atmosphere. And understanding where these extra emissions are coming from is pretty important. And one of the ways that we can kind of get a sense of that is by looking at denitrification in these marshes. And so I have this little graphic here. This is essentially just showing how denitrifiers within the marshes start to convert more reactive types of nitrogen that are introduced into the marsh from usually human activities like nitrate and nitrite, slowly converts them down to our unreactive nitrogen gas, which makes up a majority of our atmosphere. We want that. But the issue is we start to see that something is impacting this last step. The reason why studies have a harder time understanding nitrogen cycling versus carbon cycling is carbon dioxide and methane are the end products of their cycle. They are what they're trying to get to, the microbes, essentially. But when it comes to the nitrogen cycle, and especially in terms of denitrification, we're actually trying to get to nitrogen, but we're seeing that nitrous oxide is still being leaked as an intermediate product. And so my question is salinity impacting this? And so naturally, that means the objectives of my study are to both provide clarity on how changing salinity can influence nitrogen cycling and nitrous oxide emissions, and also determine in general how greenhouse gas emissions, including carbon dioxide and methane, are impacted by these changes in salinity. And here's a lovely photo of me after my first venture into the most saline marsh we went to down at Stowe Creek. As you can see, I did not come out unscathed. So, so the way that we were replicating this at Villanova was by creating a simulated salinity change. So essentially 4 sets of tanks were set up in our greenhouse. About 100 cores were collected from 3 different tidal marsh sites along the Delaware River, 1 freshwater site and 2 brackish sites, 1 more saline than the other. And then once they were brought back, all of the cores were appropriately divvied up into each of their respective tank sets. So each site's cores ended up going into each of the different types of salinity. 3 of these salinities were based off of the natural salinity that was measured at these particular sites. So our freshwater site was Rancocas Creek. So all of these cores are subjected to 0 parts per trillion and seeing essentially, is this changing salinity going to do anything? And then of course, in real life, the marsh is undergoing a tide. It is a tidal marsh. So the way that we were replicating this, as indicated by this little orange connector between the tanks, is that a series of timers and pumps were set up to allow for a low tide on one side of the tank for 6 hours while a high tide was occurring at the other side of the tank. And then after 6 hours, it would flip and slowly the high tide would start migrating into the other tank, low tide, and then the low tide becomes higher, high tide becomes lower. And so this was done over the course of 12 weeks. So there were 5 time points along that. The first couple of time points were closer together because we had an assumption that we might see change sooner and maybe not as much later once they're introduced to a new salinity. And so the cores that we were sectioned out into 4 different parts. So the top 2 layers of the soil, as well as 1 kind of middle and 1 towards the bottom, just so we can kind of get a sense of greenhouse gas emissions over the depth of the marsh soil. And so each of these sections were appropriately divvied up into a bunch of different vessels, but for the purpose of this talk, I can't go into all of them. So we're going to focus on these 3. And so we had 1 measuring our more natural emissions. So this is our carbon dioxide and methane coming off of it in general. And then these 2 are what allow us to look at denitrification rates. Unfortunately, you can't look at actual denitrification rates in the lab because you can't really easily measure nitrogen coming off of the soil. So we had to do a bit of a combo of strictly nitrous oxide coming off, as well as inhibiting that last step, like I showed you beforehand in denitrification, and having the nitrogen and nitrous oxide just stay as nitrous oxide. And comparing these 2 allows us to have an understanding of what's going on there. And so here are some of my photos of the various things that, various equipment that I use. So here's some of my tanks set up. You can see my gross little cores connected in their tanks. All of the cores were sectioned in this glove box to create an anoxic environment. And then once they were divvied up into their incubation jars, you can see I have all of these syringes collecting the gas samples. And so as it stands with COVID, naturally, as we've heard a few other times, it did set me back a little bit. So I am still only in the process of looking at the data visualization. I haven't even hit data analysis. Once I hit analysis, I imagine I'll have an even more of a story to tell.
Macy, you have frozen. Did you want to turn your screen off? Wait, or your camera off?
This is so difficult. Can't wait to see the results.
It looks like she is going to try to get back on. So if we still have a couple minutes left in her presentation, so if she's able to jump back on and wrap up within the next 3 minutes or so, hopefully she can do that, and we will advise her to keep that camera off until she finishes up.
Great. Thank you, everybody, for your patience. Do we want to maybe take a couple questions in the meantime, Leah, or
Yeah, we can do that.
Caitlin? Caitlin's been monitoring, so maybe Judy, Danielle, and Feng Wei, pull your mics off, and maybe we can do that in the interim.
I did just make it back. I don't know if you can hear me.
Yes, we can hear you. You have about a
So
minute
sorry
left, I
about
think.
that. Okay, I can jump through the rest of it pretty quickly.
Yeah, Macy, you have about 2 minutes left, so I would just keep your camera off, but if you want to share your slides from where you stopped, that could work.
For sure. Yeah, so essentially Rancocas, our freshwater site, had the lowest amount of denitrification happening naturally at the site, while our most saline site, our Stowe Creek site, had the highest amount. There can be a couple of reasons why this is happening. It may have something to do with the amount of organic matter that's in the soil. So Rancocas, even though it had the highest bulk density compared to our Salem, which is our middle saline, and Stowe, which is our highest saline, it ended up having the lowest total organic matter available for these cycling processes to happen. So that could be why we see a little bit of variability there. And then looking at all of the data at once, as you can see, this is a little bit crazy until I can actually do some stats themselves. So to try and make it a little easier, we can see that a lot of the response is happening here in terms of denitrification reacting to changing salinity. So instead, we focus more specifically on those exact time points. So Rancocas, again, kind of crazy, a little all over the place. And this very well may just be due to the fact that there is low denitrification happening in the first place and low amounts of organic matter. And so I'm indicating where the natural salinity is there. And then with our middle saline site, we see that our highest amount of potential denitrification is actually happening here during the first week, but during the 3 weeks after the fact, it's a lot more flattened out. So we see as the salinity changes, the microbes are reacting more severely, essentially. And it's the same story for Stowe. So the 10 parts per trillion is where our regular salinity is usually at. And again, we see the highest potential over here at 10 parts per trillion for that first week, and a decrease in salinity here, indicating that the microbes are reacting. And then here we see a little bit of a lag effect because it took longer for that change in salinity to hit the bottom layers, but which is why the microbes are reacting more here. But for the most part, it's also flattened out. And then my next steps are essentially to look at the data analysis and actually get a sense of what the full story is. I also have, greenhouse flux to look at over the course of time. And then finally, I have some supplementary data, including the ammonium pool and that organic matter that I already showed you, which should also help give me a sense of the full story that's happening with the nitrogen cycle. And then my acknowledgements, I want to really thank Erin Johnson, especially, who is our lab tech in Dr. Weston's lab, because she more or less kept me from drowning in mud over the last several months. And then my committee members, Dr. Rodriguez and Dr. Boshi, the Weston lab for helping me out, and then of course Villanova for providing the funding for that. And then that's it.
Thank you, Macy. That was very, very interesting, and we look forward to the rest of your results. And you'll have to come back and tell us all about what you finally learned.
Yes, sorry about that.
Don't worry about it. You did great under pressure. It's not easy. This is a difficult time and everybody's with you. We're so excited to have you present with us. And so lastly, but not leastly, I'd love to invite Roger Wang, who I believe is with us now. Dr. Wang, Roger, why don't you turn your screen on and start sharing your presentation? Roger is an assistant professor in the Department of Civil and Environmental Engineering at Rutgers. His research group is aimed at developing numerical models to connect big data and decision-making in civil and environmental engineering systems. And he's going to talk to us today about satellite-based monitoring of Delaware Bay surface area. So you can take it away, Roger.
Thank you, Marjorie, for the nice introduction. And thank you very much today for organizing this event, and I really enjoyed this conference. So today I would like to talk our recent work on the satellite-based monitoring of Delaware Bay surface area. I'm Roger Wang. I'm assistant professor at the Department of Civil and Environmental Engineering, Rutgers University. So as we see in the past century or decades, we have seen that multiple things are changing in the estuary, especially in the Delaware Bay. If you see on the left, there's a paper talk about the tidal range in the last century, more than 1.5 centuries. So you can see the amplitudes of the tides is changing in Philadelphia, and especially in the last century, the change is positive, and it's very dramatic in the past century. In comparison, if you check the tidal range in Sandy Hook and Lewis, Delaware, the tidal range is not changing that much. So that tells us something is fundamentally changing in Delaware Bay. Another thing is the area of the tidal lands. I found a recent paper. They surveyed the area in Delaware and found the estuary is losing the area of the wetlands in the past 2.5 centuries. You can see comparing 1700, and now you can see that the change is dramatic, and until recently, we can see there's a very deep valley in the area of wetlands. So given this fundamental change and this evidence, we are curious what really happened and whether we can use the new technology to check the change. One thing we tried is, for the reason for these changes, there's a very good review about the estuary dynamics in the past century. So what's really fundamental is both natural and human factors here. First of all, as we compare the modern estuary and the historical estuary, we can find that there are less snowpack, and the river has changed their course. Reservoirs and infrastructures are building up, so they are changing the roughness of the bottom of the river and estuary, and also the bathymetry of the river is also changing. Additionally, the natural features are removed because people are developing urban areas, and also the dikes and the infrastructures are changing the landscape a lot. The inlet of the estuary is also changing, and also there's boundary forcing change like sea level rise, ocean swell, storm surge because of climate change. So we can see that given these changes, there's a very strong alteration to the hydrodynamics inside of the bay. So we are curious how we can see from the space. We are based on the USGS dynamic surface water extent product. It's based on Landsat satellite, level 3 product. The resolution is 30 meters. It's the history of this satellite is very good. So it can go up to 1982. And generally, if we analyze the data, we can see that we can classify the land surface area into different categories. For example, for 1 and 2 category, we find that there's water with high and moderate confidence. And 3 and 4 are for the potential wetlands and the water and wetlands with the low confidence. So given this, we group 1 and 2 together as water area, and 3 and 4 together as the wetland. So we are curious how these areas change over time. We are focusing on the Delaware Bay, so also including some adjacent counties, try to look at the wetlands in this area. You can see the upper stream boundary we set to the tidal gauge station and also go to the mouth of the NOAA's tidal stations. So we want to focus on this area, try to look at the change. Here is the sample data. As you can see that the orange area is the water area with high confidence. Blue area is the water moderate confidence. And the green, dark green, and the light green areas are the, we group them together as the wetland area. So want to track the change of this. In dealing with this data, there's multiple data quality issues. The first of all, issue is the incomplete imaging. Sometimes the satellite data has some noise, has zigzag boundaries. So this due to the either the sensors in functionality or there's other issues with the data transmission. So data sometimes is incomplete. Also, cloud coverage could be an issue because Landsat is optical sensor-based satellite. So cloud coverage could be a issue. Also, given these issues, there's a question, is there enough data to resolve the surface area? So we need to really check every image we obtain through the Landsat satellite and see whether which data is usable, which data too much cloud or too much noise there we cannot use. So generally speaking, we only pick those cloud coverage lower than 30%. And also those from those noise, if the noise are doable, manageable in data analysis, we still use that, especially when we combine, because there, when you scan the area, there are also multiple images, not only like one complete image like this. So when you combine them, sometimes we pick up they have some overlap, so we pick up the better quality data. In this way, we can also reduce the noise. Using this way, we found out that generally speaking, every year we have 5 to 12 images. So at least one for each quarter. So in average, we have 8 pictures per year. So we can take average for the year. Here's the result through year 2000 until now. This is the mean water area in square miles. So we can see generally it follows, it stay in the same at the same level, but we can see that there's some up and down, especially one trend is the 2004 to 2006, which coincident with the Delaware River flood in that year. So which is an interesting coincidence, but we don't know whether there's a fundamental reason behind it. There's still preliminary data. And also since that valley, we can see there's a steady, slow increasing trend. So which could be due to the sea level rise, but we still need to take closer to the water level data and see whether there's a strong correlation between this or whether the slope of this data makes sense. Second, we are checking the wetland area over years. We can see that as multiple reports talking about the surface of the wetlands, generally there has a decreasing trend until 2017. So I think this data is new compared to the paper I found earlier, which is only up to 2000. So recently, it looks like the surface area has a steady decreasing trend. There's two strong events I spotted. One is Hurricane Sandy. You can see that after 2012, there's a dramatic drop of the wetland area. And also in 2016, we see another. These two events could be due to the strong storms events, which destroyed the wetlands area and make the drop of the value. But interestingly, since 2017, we can see there's a flat and even upper trend. Especially last year, we see a very strong trend, even though the uncertainty is larger here, but we still can see the trend is obvious. We are still trying to understand what's happening there. This is still our preliminary data. We are trying to next looking at how we can extract the spatial distribution of the water and the wetland area. And we are trying to use mode decomposition and other data-driven analysis to look at how the dynamics of these water and wetland area changes. And also another student is working on the tidal dynamics in Delaware Bay, and hopefully we can combine the water level data and this surface extent data together and have a better story about the reason behind these changes. So to summarize, I think what we found is from the satellite data is that there's a slow increase of the water surface area since 2005, Delaware Bay, and the wetland area generally decreased, and the decrease becomes significant after storms. There's a recent recovery of the wetland area. We are still checking whether it's a data or there's a whether this is a real trend. So at last, I would like to thank the student, Catherine. She has done most of the analysis and also the funding support of the Institute Earth, Ocean, and Atmospheric Science at Rutgers University. Thank you very much.
Thank you, Roger. That was very interesting. And I want to invite all of our speakers to turn their cameras on and unmute themselves as we move into Q&A. I've also been asked to remind you that there are two, I believe, Danielle, correct, poster sessions that are associated with this panel. So please avail yourself of those. We love to see the emerging research that's coming from our students. And so now I'm going to ask Caitlin Tecker from Partnership for the Delaware Estuary to moderate the Q&A because she has been following the very, very active questions that have been coming through the Q&A and some through the chat box. So Caitlin, I'm going to turn it over to you to take us home. Thank you.
Thanks so much, Marjorie, and thanks to all of our panelists for such a great session. We did have some questions come in the Q&A box, and I'll ask those now. Feel free to chime in if the question isn't directed at you, but you have a comment to say. First, we're going to start with Dr. Wang. A question came in from Desmond Khan asking about the deepening of the shipping channel and if that could be contributing to the influence of tidal amplitude at Philadelphia, maybe more so than climate change.
Yes, there's a likely reason, but hydrodynamics in shallow water could be very complicated. I think the paper I show here, Talk and J, is a very good summary of what people discovered so far. There's a lot of dynamics, and we hope we can also do some significant work in this area in the future. Thank you for the question. If you need more details of the information, please feel free to send an email. We can maybe have a longer discussion on this. Thank you.
Great, thank you so much. A second question came in from John Callahan. This is for Danielle or Feng Wei. For coastal marshes to keep pace with sea level rise, sediment supply is important. For the lower estuary, does the sediment primarily come up tides or through surge or through upland runoff? And is the upland sediment supply decreasing?
Right, I'd jump in and say there is a sediment chapter in the TREB report that I talked about, which indicates that the river runoff of sediment, the sediment in river runoff has been decreasing. But for coastal wetlands surrounding Delaware Bay, that is probably not the main source of their sediment anyway. That would be a source of sediment for freshwater tidal marshes in the upper part of the estuary, which, you know, have more access to sediment from the rivers. But down in Delaware Bay, most of, you know, the regional sediment management plan shows that fully half of the sediment supply for the whole system is coming from eroding marshes. The sediment budget is only currently in balance because of the sediment supply from eroding marshes. So there's this factor or this phenomenon called marsh cannibalism, where the sediment you're getting to add to the surface of the marshes are accreting partly from sediment from eroding marshes. So you have dwindling, you know, erosion is fueling a lot of the sediment supply in the lower part of the system. There's a lot more I could say about how that relates to dredging and maintenance of those systems, but there's a lot more frequent dredging of those tributary channels because of the eroding marshes. Not sure if that answered it.
Dr. Chen, did you have anything to add?
I don't have much to add on the data side, but the sedimentation is a very important factor when you're evaluating the impact for the future sea level rise. So my impression is under current condition, right now, the sedimentation rate is about at the same pace as the sea level rise, so that they balanced. And that's supported by the report from Judy and the NJSAP report 2020. And I think from those set measurement, they have like observed like 1 to 6 or maybe even higher millimeter, the millimeter per year sedimentation rate in the marshes. I'm not sure where the source is, but my impression is majority made from the marsh itself, organic matters. But yeah, we will look into more details on that.
Another quick factor on that is past management practices. So diking has effectively robbed a lot of those marshes from sediment supply for long periods of time, which affects their elevation capital, or they're sitting low relative to what they would have been if they were not managed. I think Judy talks about this in her book quite a bit. There's a lot of folks who have focused on this.
Thanks. There was another question for Dr. Wise from Desmond Kahn. Desmond is asking, has the DEP committee looked at the impact of the large volume of Roundup used in frag removal?
Oh,
No, we didn't look at Roundup. I know I've read a lot about the herbicide, and it's certainly a very damaging toxic chemical for a whole lot of things beside plants. And it's, you know, I think we need a paradigm shift in the attitudes of the marsh management people towards Phragmites. I mean, it is such a negative thing. The information about Phragmites building up marshes is not new. That's over 20 years old. And that has had, and also the, you know, the information about reducing pollution, the information about it being okay as habitat rather than terrible. And every, you know, the marsh management community is knee-jerk, it's frag, we got to get rid of it, it's bad. And this is, it's time to change that. And I don't know how we do it. We have a problem with the marsh management community, as someone once said to me. I get paid to kill Phragmites. I don't get paid to leave it there. And I think that may be one reason that is driving their continued resistance to considering Phragmites as something that ought to be left alone in some places sometimes, particularly places that are in trouble from sea level rise.
I'd like to comment on that, but we think a lot about that as well. What are you managing for? If you're managing for fish and wildlife habitat, if you're a refuge, it may be a more important thing to restore Spartina. But if you're managing for coastal flood resilience or carbon capture, frag is not bad, right? And so
it's much better.
Right. And so a lot of money does get spent on frag eradication, and arguably for different types of management goals, a lot of money could get spent on preserving the marsh that provides coastal resilience or carbon capture.
I'm going to take just a moderator's prerogative here and just raise the issue of the fact that I think the question about what you're managing for is really important. And then there's recent data that talks about impacts of frag to coastal forests that we're losing. So I think it depends on where you are in the location, because of the question about marshes changing and moving more frag inland. So I think there's just, it's a to be determined in some locations, perhaps.
Yeah, thank you so much, Judith and Danielle, for your answers, and Marjorie for that point. Definitely something to be thinking about. A question came in for Macy from Carrie St. Laurent. Macy, I'm not sure if you're here. I hope you are. Hey, Macy. The question is, how do you expect your results to change if you could alter, I'm sorry, excuse me. How do you expect your results to change if you could also tidally vary the salinity under different ranges?
That's actually a pretty good question. And so that's kind of an aspect that we had a little bit of an issue with in terms of the experimental design, is how many aspects can you replicate from the real world? I will say, even though I had specifically 4 treatments of the 0 to 5 and 10 parts per trillion, in the real world, when you have an experiment going for 12 weeks, they don't inevitably stay that way the whole time. So even if unintentionally, I did actually have some variability in my salinity for the data. And so typically though, I also saw that someone else had a question because they missed the relationship between nitrogen. So as a way to tie that in. Typically, though, you see your highest rates of denitrification occurring at the naturally occurring salinity, because this is what the denitrifiers are used to. That's where that's the salinity they're happiest in. And then as time wears on and salinity starts to change, and especially intrude into the lower layers of the marsh as well, that's when we start to see that denitrification changes. So how productive that particular pathway over time, as the salinity it starts to level out. Oh no, can you still see me? I just got an internet connection unstable. But pretty well over time, you start to see that the microbes will adjust regardless. And, you can even see that with salinity rise, we might actually start to have where the microbes adjust to this increased salinity and start producing more greenhouse gas emissions, which could be a problem. Hopefully that answered the questions.
Thanks, Macy. Another question came in later during the panel, and so anyone can answer this. Is there a specific area that sees more increase in water than others, or more marsh loss than other areas of the estuary?
Well, in TREB, again, this is my big commercial for the technical report, we do show acreage loss rates by sub-estuary zone. So on Delaware Bay, there's 2 sides of the Delaware side, 3 sides of the New Jersey side, of course, in the upper estuary of New Jersey and Pennsylvania. So we show, what the National Status and Trends and NOAA Landsat CCAP data show for those different sub areas over time. So those data do exist. Predicting into the future, as many people have indicated, and Judy talked about it, is a little more nuanced because of the coastal squeeze issues and lots of hydrodynamic variability, sediment supply variability. I mean, Delaware gets more sediment coming down the river than New Jersey side. So most of the marsh loss has been on the New Jersey side of Delaware Bay. And we think that there's probably more of a sediment deficit to the New Jersey side than the Delaware side, but there's lots of local variability, lots of local subsidence difference even.
Couple more minutes left here, folks.
Okay, I'm going to wrap up then with just one final kind of overarching question that I had while listening to these great presentations. When do we expect to reach the tipping point for marshes if we haven't already? And when will we know that we've reached it?
I talked about that. I don't want to keep talking. So again, we talk about that in TREB. That is going to be very locally variable. Again, up in the upper estuary where your freshwater tidal marshes, their ability to keep pace with sea level rise is much higher, but they have other threats from development and there's other types of things going on just beyond sea level rise and even salinity rise. Management, set practices, armoring, our commitment to preservation of those habitats. I mean, in Pennsylvania alone, we lost half of the acreage in the National Wetland Status and Trends from the 1970s to current time, not from climate change or sea level rise, not from erosion, but from just conversion or the failure of no net loss policies to protect those habitats. So, but down in Delaware Bay, it's very locally driven. The dynamics of the plant community and what govern elevation capital is partly sediment supply, partly organic matter accretion and, capture and management practices.
Any other thoughts from our panelists on that? No? Okay. Well, thank you so much for this discussion. And thank you so much to the attendees who submitted questions. I'm going to hand it back over to Leah, who will wrap up for this session.
Thanks, Caitlin, and I will just echo that. Thank you to all of our attendees and thanks to all of our great speakers for showcasing your research today. I will just reiterate that we do have 2 great student talks that are included as part of this session as well as posters. I did include the link to our posters on our website earlier in the chat, but I'll post it again here. I encourage everybody that's still in the session to take a look at those when you have the chance. We do have one more poster session that's going to be taking place tomorrow morning from 9 to 10. And I'm also going to post a link to all of our sponsors and their Sched page. So you guys can check those out as well. And I will just reiterate again that the virtual summit would not have been possible without support from our sponsors. So we do encourage everybody to go take a look at both of those links when you find the time. So we will rejoin at 1 o'clock for another one of our climate panels featuring the AC3 and meteorologist Glenn Hurricane Schwartz. Everybody have a good lunch. Thanks, guys.